we're looking at equivalent thermal conductivity. So we just saw the series and parallel concept. Now we are trying to get an expression for the REs. So we are trying to, this RE is there, right? RE equivalent. For this K1, K2, that is your constant, right? Material constant. So equivalent thermal conductivity constant. So an equivalent value, right? How we, so basically figuring out resistivity, equivalent resistivity. So when we have, let me actually help you guys with this. I think this will help you. See, basically in topic of electricity, actually we have not done this as in your 9th or 10th grade. We have not done this. See, R equivalent, you can figure it out with R1 plus R2 and all of this. See, R1 and R2 and all of this will have their own rho 1 and rho 2. So similarly, can't R equivalent have its own rho E? We have not done this, but can't it have it? It can, right? So similarly, over here, we are looking at your K equivalent, that is thermal conductivity equivalence. That's it, nothing fancy. So let me read through. It's actually, the write-up is decent enough for us to understand. See, when you have a system made up of two or more material, we often replace the whole combination by one equivalent slab that has the same total length, same area, and that transfers heat at the same rate. This allows us to treat the complicated system as a single slab with an effective or equivalent thermal conductivity. So it basically makes our conversation and the job easier, the math easy. Application is quite a lot. It's left to your imagination. So it will help us, say, let's stick to a simple thing. It will help us in some mathematics. Okay. So we need to figure out the entire system's conductivity. So we do this and then we take that value and put it in somewhere else and so on and so forth. So the basic idea is equivalent thermal conductivity is the overall thermal conductivity of a composite system. It answers the question, if this entire arrangement were replaced by one uniform material, what would its conductivity need to be to transfer heat at the same rate? Right? It makes sense. So all these fancy words tells that I just want an equivalent, rod which does the same. Right? All this work is done by a single rod. So official definition is that for any combined conductor, we define K equivalent such that the heat current through the actual system equals the heat current through the equivalent slab. So H actual is equal to H equivalent, and this is given by this expression. So let me actually derive it out. So that will make more sense. Okay. So first we'll start off with series connection. So we'll start off with series. Series is quite simple. So we have R equivalent is equal to R1 plus R2. And this is nothing but L1 plus K1A plus L2 plus K2A. And this is total length L, right? Divided by K equivalent into A. So here A gets cancelled. And here L has to be L1 plus L2, right? Total length. Basically you are connecting series connection. Okay, I think I'll draw it and show it to you guys what I mean. So if this is the source and this is the sink, and we have rod 1, right? The same thickness you should have rod 2, but the length need not be same. L1 and L2. So equivalent rod is this, for example. Here it has to be the same length. Sorry, total length has to be L1 plus L2, right? So this has to be L1 plus L2 because it has to move from one end to another end. That distance will not change. The source and the sink are not moving. So L has to be L1 plus L2. Area of cross section has to be same as this. It's same for all of them actually. So A I can connect and cancel, not connect. So basically I have 1 by K equivalent, actually L by K equivalent. So if I have to flip it around, right? So for that I need to, I'm thinking of optimal representation. No, this won't help. For many, then it will be kind of confusing. Divided by K1 plus L2 by K2. So basically your L divided by L1 plus L K1 plus L2 by K2 will give me K equivalent. So in general, our formula will look like K equivalent is equal to summation of, or L being the total length, summation of Li by Ki. That's it. And L here is summation of all the lengths. So that you guys can, yeah. So that will be your final expression for series, right? Now let's look at parallel. So in parallel, what do we have? We have, okay, for parallel, we have to go the other way around. We have to go with the voltage and stuff. Remember? So series, we can do that. For parallel, so I'll start with heat current. So heat current for the first one is K1 A1 delta L by L. Because remember, the source and the sinks are directly connected. Every rod has the same length. Area of cross section can be different, and K value will be different. K2 A2 delta T by L, length has to be same. Now the total heat that moves from one end to another end is given by K1 A1 plus K2 A2. All of this has the same delta T by L. So I am taking common. Again, I'm skipping steps. See, basically this is the heat. So let me actually write it systematically. Not very happy with it. So we are looking at a source and a sink connected with different rods. Say this is one rod, this is another rod. So in this case, both should have the same length. Area of cross section can be different. K values can be different. So individually, the heat current by, so this is the case of rod 1. This is the case of rod 2. So this can be your rod 1 and this is rod 2, for example. So the total heat that will transfer from one end to another should be sum of, right? Should be sum of that. So H total has to be sum of H1 plus H2 for this case. So heat moving from the source to the sink has to be sum of each contribution. Do you guys agree? That's all I've written over there. So now if I have an equivalent heat, so we have K equivalent, and this should have the, say, sum total of these two areas times of delta T by L. That will not change. So this will be K1 A1 plus K2 A2 times of delta T by L. So this and this will get cancelled. And then what else can we do? K equivalent, that's it. There's nothing much we can do. Is equal to K1 A1 plus K2 A2, this entire expression divided by A1 plus A2. So now in general, we have K equivalent is equal to sum of Ki Ai divided by sum of Ai. And that's that. Right, I think, okay, that's the math, that's it. So that's how you get out the equivalent thermal conductivity.